Okay, let's take an example. Let's suppose we have a population and a sample, and let's suppose population have uh, total number of things to be 10, and among those things, let's suppose we have considered the categories or the things which have a desirable characteristics to be m. That means m are the number of things that have those desirable characteristics, and they are 4 in this population. Similarly, n minus m refers to those of things that do not have that desired characteristics. Now let's suppose among that population, the sample that we have taken has total number of 3 items, and among them the items with the desired characteristic is 1 and others are 2. In that condition, the probability of getting this the thing with the characteristic value or the desired characteristic, the probability of that is given by 2 by 5. But in that same population, if we take a single sample, then the probability of getting this desired characteristic item is 1 by 3 only. That means we have change in our probability. Similarly, even if in this particular example, even if we don't take population but rather different samples, then according to the number of samples, we can have different probability for each of them. That means now new scenario has been arised where the population does not have the same property or does not have the same probability for different events. For the same events, so as you can see, a new scenario has been arised that the probability has been changing even for the same desired characteristic. For example, if we imagine the probability of drawing some items that has a desired characteristic to be a success item or to be a success, and drawing other items we do not have that desired characteristic, if we consider that event to be a failure, then we can see the probability of success as well as failure both is changing according to the amount of the numbers or the amount of things that we take. That means in a similar way, in a simpler way, we can say that the probability of success or failure is been changing continuously on the basis of the samples taken. Now, in such kind of scenario, we cannot use binomial or negative binomial theorem distribution, and we have to introduce a new kind of probability distribution which is known as geometric probability distribution, hypergeometric probability distribution. So this is applied when probability of success does not remain same in each trial. So the PMF, the probability mass function of this distribution, looks something like this. Now the method of drawing the items from a population or sample is same as I had said earlier. So let's not go to the derivation part of it because it's pretty easy. So let's try to interpret it. What does it mean? Okay, so we have px equals mx. The Now this can also be written as a combination form, which it is that if some of you like to think in combination, this might help you. So it's a product of two combinations. First combination says that the total, so x here represent number of success. Now here the number of success, the meaning of number of success is quite different. Success means the probability or number of times an item with desired characteristic is taken. This is what the meaning of success is here. So the meaning of success has also been changed. So x x is this, and so now m is the number of items with the desired characteristic into the population. Now from those m number of items with the desired characteristic, we choose x. This combination says that, and this combination says among the remaining items in the population, we take this into the sample. So this is what the geometric distribution is suggesting. Okay. Now, after understanding this, it is very crucial to understand the mean and variance of this distribution. And for that, let's see the moments. Let's see the moment genetic function of it. But it turns out that the moment genetic function of it is not very feasible, because as we can see, both terms in here are just the probability term, just the combinations or just the numbers. And since both are numbers, it doesn't be quite helpful to derive the uh, moment genetic function. That's why instead of deriving moment genetic function of it, let's go directly to find out the moments of the function. And we can do that by using expectation. Okay, so expectation, this is the definition of expectation. Now let's put this value in here and let's see what happens. So we get summation x equals 0 and x mcx n minus mcn minus x. Now what can we do here? So yes, so what we can do is we can use some properties of combination, and that is to write this. After this, since we have x here, and x factorial can also give us x, so that we can cancel them out, we can write m factorial m minus x factorial x times x minus 1 factorial, and it is remained as it is. Now from here, this x and this x are cancelled, so we are left with summation of x equals 0 to n m factorial m minus x factorial x minus 1 times n minus m n minus x. What next? What can we do next? Now from here, we have got x minus 1, so we can write m in terms of m minus 1. That is summation x equals 0 to n m minus 1 m times m minus 1 factorial m minus x m minus x minus 1. Now we can write this minus 1 here, but it isn't making much difference. Factorial this. Now after that, yes, so we can write, wait a second, yes, okay, so we can take m by wait, I think I missed something. Yeah, I missed the denominator value NCN. Sorry for that, but the probability density function, sorry, probability mass function also include this uh, derivative term which is free from x. Okay, very sorry for that. So let's suppose this to be x, and let's suppose this to be z, and let's take it out from, okay, so we get m and we get m minus x there. Now again okay, we have got m minus x. Okay, what do we do with, what to do with that? M minus, sorry, this, okay, wait. So I think we can get, okay, we don't need to do that. We can just keep it as it is. We just took m from there. That means we got z m summation x equals 0 to n m minus 1 factorial. Then what? M minus 1 factorial, and we have got sorry, m minus x minus 1 factorial, n minus m n minus x. Now this can also be written in terms of factorial, right? And I think we can do that. Yeah, we can write it in the form of m minus 1 c x minus 1. I think so. Yeah, we can write that. Then n minus m c n minus x, and here m by actually z is 1 by ncn, so we got ncn. Okay, so we have got a value of expectation of x, is m by ncn summation x equals 0 to n of m minus 1 c x minus 1 and minus m c n minus x. Yeah. Now from the property of the combinations and summation sign, we can write this term. Is n minus 1 times c n minus 1, and when we write that, we get the ultimate value of expectation of x is equals to n by ncn times n minus 1 c of n minus 1. Alright. Okay. But since this is also a combination, both are in n and both are in small and capital N, we can further do it. Okay, so we can write it in form of n minus 1 factorial n minus 1 factorial. These are cancelled, right? So we are left with, okay, let me write it. Okay, what is 1 by n? You have opened this bracket to plus, cancelled, n minus n factorial times n minus n factorial. These are also cancelled, this become 1 times m. Sorry, and we have got n here, we have got n here, so we have got m by n, is it? Yes, so we have got expectation of x is equals to m n n. This is our mean in hypergeometric distribution. So this is about the mean. Now similarly, we can also find out the variance too. Okay, let's see how do we find the variance. So one thing that is added is that we cannot find the variance by simply putting expectation of x squared, but we have to put something like this: expectation of x minus 1 plus x, and if we do so, we can use the properties of exponential and distribute the exponential to both the terms, and we get exponential of not exponential but expectation of x times x minus 1 and plus expectation of x. Now let's first find out expectation of x squared, because we have already found out expectation of x. Okay, so yeah, after it's okay, so we can use the same thing. We can use the definition of expectation now, which gives this. So let's put the PMF: summation x equals 0 and x minus 1. What is PMF? PMF is PMF is MCX n minus MC n minus x by NCN, which I had forgotten in the previous case. But I'm just saying that z equals 1 by NCN. Okay, and I'm just adding this. Now since it's a constant, I'm taking it out. Summation x equals 0 to n x minus 1 m minus 1 m minus 1, wait a second, m times m minus 1 factorial m minus 2 factorial by x minus 1 x minus 2 factorial times n minus mc of n minus x. G m minus 1, yeah, then we got x equals 0 to n minus 1 times, this are cancelled, so we got factorial, this. Yes, this. So, what next? Okay, so we have got this. Let me check. Okay, m minus 1 by this summation of this times this. So I think we are pretty much done. But from the property, so we can write it in the form of m minus 2c n minus 2, maybe x minus 2, and then according to the formula of the product of two combinations, we get z m minus 1 times this and this. That is what? Okay, wait, what? N minus 2. Yeah, yes, n minus 2 n. Yep. So you can write it in form of n minus 2 c n minus 2. So if we have expectation of x minus 1 equals m minus 1 n c n minus 2 c n minus 2. So it gives us m minus 1 times n minus 2 factorial by n minus 2 factorial and n minus 1 n minus 2 factorial by n minus 1 n minus 2 factorial. So these and these are cancelled, these and these are cancelled. I got m minus 1 and n minus 1 and n minus 1. So we can write it as, okay, I think we have z2. No, we have z has already been used, so we have got m by n minus 1 by n minus 1 times n minus 1 times n. Is it? Let me check. Yeah, so this is the thing. So this is the thing. Yeah, this is what we get for expectation of x at minus 1. Okay, since variance is expectation of this plus this, and we have already found it out, and that is, I'm not going to write this, but write the variance of x. Is it the variance? No, it's not the variance, it's just expectation of x squared. Square equals this thing plus expectation of x. What was it? It was n times n by m by n. So let's rearrange it. We have m by n. So we can take m by n is common and left m minus n minus n and n minus 1 plus n. So m by n minus 1 and n minus 1 plus n minus 1 and this. Then after, I think we are done with this pretty much. Yeah, so this is what the variance is. No, this is not the variance, it is x squared Now expectation of x squared we have got. Now then after variance is given by expectation of x squared minus x full squared. Then that means minus of n squared by n squared. Yeah. Now after finding that, this is now variance. I'm not going to simplify it any further. This is what we get. This is the crude Vx variance of x in terms, not in terms of, but in case of hypergeometric distribution. Okay, so this is all about the moments. Now let's see some properties and uses of it, of this kind of distribution. So the properties are: the mean is n, m by n, variance is as it is we have seen here. Then okay, so variance is actually pretty condensed here, and okay, so we get, if we rearrange and manage it, if we manage it properly, then we are going to get n minus n by n minus 1, n m by n, n minus m by n, and this is it. So now this is, we know, expectation of x, mean, variance, n minus n by n minus 1, expectation of x, n minus n by n. So this is it. This is the variance. Now some properties include this, and hypergeometric distribution tends to binomial distribution when n tend to infinity and m by n is equals to pi. So it says that sorry for that. So it says that when m by n tends to p and n tend to infinity, then hypergeometric distribution tend to binomial distribution. Is it? Yes, binomial distribution. Okay, so these are some properties. So this is it. This is all about hypergeometric distribution.